Well, I can't really ask if people can see, but today I'm going to do a problem that confused me for a while, honestly, and it's like a multiple part program that requires a little bit more thinking. Honestly, when I first looked at this type of problem, I looked at the solutions manual after, and then I was just like, okay, why don't I just memorize kind of how to do it? But today I'm going to go through how I've learned to think about it so that it makes some logical sense. So the type of problem that I'm going to do is, can it be seen? The time derivative with respect to u is equal to some diffusion constant times the diffusion term plus u times some constant, times the quantity of that. And so I feel like this can best be discussed in the context of an actual problem. So why don't I let, my cursive is awful. Why don't I let d is equal to, let d be 3, and then a be 2. And so if we write it out again, we have time du dt is equal to 3 second derivative with respect to x of u plus u times 2 minus u, where, as you might have guessed, u is a function of both x and t. Okay. So, well, first, to make this an actual problem, I'll set initial conditions, and I'll just choose something random like u of x of 0 is equal to 1/3. Okay, is that visible? Yeah. And so, if you say that, the first thing I usually do is I look at this term, and then I say, oh, why not just set it to 0 because it looks interesting? Which, this is originally what I did, and then I memorized from there. But I've discovered why it is the case that it is. So then we have u times the quantity of 2 minus u is equal to 0. Then we have u is equal to 0, and u is equal to 2. So let's discuss these two solutions. Let's say we have no idea what happens at 2. So why don't we figure out what happens at u is equal to, at u is equal to 0. So at u is equal to 0, this entire term cancels out, and we just have diffusion. And based on our initial condition especially, it's not significant in any way because we start at 1/3. So if u starts at 1/3, we'll never get to 0. So it's pretty much insignificant. So we know that there's something that happens at u is equal to 2. That's all we have right now. And so I think the rest of it can best be seen if we expand what we originally had. Ooh, moving farther. So if we write it over again, but then write it out, we have this. And so based on that, I would guess that something happens with this minus term when u is equal to 2. And so what happens is best actually seen if you split up the equation. So if you, as you might have guessed, if you just ignore this entire term right here, we have the diffusion term. So we know that something spreads. I just write that. Every point is. And then if we look at this term, these two terms, and then ignore the diffusion, I realize that bracketing this doesn't make any sense now. We get actually exponential growth. So if we use separation of variables, I'm probably skipping steps. No, this is t plus c. we do actually get some exponential growth there. What would particularly become significant? So we get from this that we have diffusion, which is obviously counteractive to exponential growth because diffusion flattens out everything and spreads it. And this one makes it go up. So we have something that wants to make it spread and another one that wants to make it up. And so we also know that something happens at u is equal to 2. And the best description of what happens is that when u is equal to 2, we find that the exponential term is basically canceled out. Because then the squared term becomes more, what is the word? It becomes more important. And it basically helps cancel out the growth. So if you did out the dominant balance like thing, you'd be able to see why it is that when u is greater, when it reaches 2, it just stays there. Because it's stuck. And so we knew that from diffusion something spread. So traditionally diffusion looks like, by itself, it looks like this. And note that there's no single derivative. That's an awful diffusion picture, but you get my point. There's no advection, so it's not moving anywhere. It's just stuck. So no advection. Which means that our centroid is at 0. And then we have this barrier that it hits at n is equal to, not n, u is equal to 2. And so it grows really fast from the initial condition, which looked like, this is 1/3, excuse my terrible drawing, but this is the initial condition. So the exponential term makes this grow. So it grows. And then it immediately dies. That's morbid. So it originally started at this. Then it grew to this. And then it kept on growing and then it flattened. Because as soon as it got there, it couldn't go any further. It's like a barrier. And so once we flatten it, then we have something that looks like this. Where the centroid is still 0, even though it may not look like it. And so this u is equal to 2. And so we know that the height is 2 because it flattens at u is equal to 2, and it can't go any further because the growth term is canceled at 2, and it stops. But it keeps on spreading over time, which is why we have change over time. And so how does it spread? Well, we would find the velocity. And the velocity is proportional to, yes, both. It is proportional to time. And the width is proportional to time. But for the actual number of velocity, it's actually proportional 4dA. Where we discussed in our problem that d is equal to 3 and a is equal to 2, which means it's equal to, in this problem, is equal to the square root of 24, which is equal to 2 root 6. And so width is just equal to velocity times time. Because if we say that velocity is actually just change in position over time, if you multiply it times time, we have the distance, which is what we want. And so it's equal to 2 root 6 times t. So if we have any problem that asks you, oh, at t is equal to 100, what does it look like? That. If t is equal to 1,000, what does it look like? Well, that, with the changes in width. Yes. So that is how I think about this problem.